Okay class, very good afternoon. We are here to start with the new chapter, that is strain energy and deflection due to shearing and bending. We will be having total 5 cases in this. Primarily we will be having up with the case of the loads, that is load due to your first of all your gradual load, your sudden load, and your third one is the falling load, that is the impact loading. What will be the impact of the deflection in all these 3 cases? And fourth one is the case of Castigliano theorem. We need to calculate the deflection through that case. And fifth one is the case of the Maxwell theorem. We have already covered Castigliano theorem. We'll try to cover these 3 cases and Maxwell in today's class. Let us start up with what is the strain energy. Strain energy is that when an elastic body is loaded, what happens at that time? There is deformation in that. It changes its shape. If we are applying a tensile force, there is an elongation, and if we apply a compression force, there is a compression in that. At that time, when body is having the elastic loading, at that time there is a change in dimension. That change in dimension is due to some stored energy in that. That may be due to compression, that may be due to the tensile force. At that time, that change in the dimension, the stored energy at that time is defined as the strain energy. Let us go through the definition. When the elastic body is loaded, it undergoes the deformation, that is change in dimension. When load is applied and the elastic body originally comes to gain some dimension, and when load is removed, it comes to its original dimension. During this time, when the load is applied, there is some energy stored, and when the load is removed, the energy is removed from the system. That is called as the strain energy. Okay. Next point. What is resilience? Strain energy is stored within the body during the elastic limit when the external loading is applied. That is called as the resilience. When the maximum energy at the time of the elastic loading, or we can say at the time of the elastic range, the externally loading is maximum value, maximum stress value. That is your proof resilience. When proof resilience is divided by volume, we get the your modulus of resilience. We'll do the derivation for the same. Let us see strain energy in simple tension or compression. We know the strain energy is equal to half the load into change in length. And now we know load change in length is equal to stress into length divided by E. Now we are having one more value, that is W, that is the load, that is equal to stress into A. We put these value and this value in this equation in order to generate the relation for the strain energy, which is simply equal to 1 by 2 stress square A into L by E. This is the relation for the strain energy, that is a general relationship, which will be further classified into 3 relations due to gradual load, due to impact load, and due to sudden load. Now, if this relation we are having area into length, it is volume. If we divide this with the strain energy, we finally get the modulus of resilience, which is the definition of modulus of resilience. That means the strain energy is basically the energy stored within the body when there is when the body is loaded externally. This is just the stored energy, strain energy. So this was the about the derivation, and this was about the definitions. Let us come to the 3 cases now. First case is that we are having a gradual load. For example, when we are applying some load onto a body very slowly, gradually we are applying the load. Okay? We are not increasing the load suddenly, or we are not applying the fallen load onto a body. We are increasing the load gradually. At that time, we are having energy due to the external load and work done by the body, work done on the body. When we apply a load, naturally there is some work done. When we apply the energy, that must be equal to the work done. So, equating these 2 equations to generate a relationship for the gradual load for the stress, that what is the amount of the gradual load. If we equate these 2 equations, we got a relationship, that is stress is W by A. That means when a body is loaded gradually, that means the load is increased very slowly from the initial 0 to the final step. At that time, the relation comes out to be load over area. Second case. Second case is your suddenly applied load. What is the suddenly applied load? When the load applies onto a body suddenly. That it is not stepwise. In the gradual, we are applying 1 kilonewton, 2 kilonewton, 3 kilonewton gradually load. In the suddenly, we are falling directly 10 kilonewton onto the required part. So at that time, we will have the change in the relationship, that is the suddenly load will be equal to 2W by 2 into load by area. The value is double in the case of the suddenly applied load. Third is the case of the impact loading. I am skipping the derivation part of this. In this, when the load, this is your road, this is your collar, this is the height h from which the load is going to follow. Now, we have applied a W load onto the collar. What happens that when this load fall onto the collar, it will move a bit downward. This is delta L, from which height it is falling, it is h. W is the load, E is your Young's modulus of a material. So we get a relationship that the impact strength for the suddenly fall or the impact loading case stress value is W by A 1 plus under root of 2H over A divided by WL. One of the value might not be given to you, and you have to calculate either the suddenly applied load or the length of the collar or the height from which is being fallen, or you may be able to calculate the area also. Whatsoever one thing must be not known to you, you can calculate out of these things. So this was all about the theoretical part of strain energy. Let us come to the numerical part. It is clear up to you?